our problem is given that z plus 6i divided by z minus lambda I is equal to I, where lambda is a positive real constant, show that z is equal to lambda over 2 plus 3 plus I lambda over 2 minus 3. Now, one of the things to consider would be just the way that this here is structured. Our goal, our vision is to get to somewhere like this, and it is structured in a way where you can see the real and imaginary are separate. But if you consider where we're already standing, where we already are, we've got lambda I, 6i, we've got an I here. All the imaginary parts are on the numerator, denominator, they're everywhere. They're on the right-hand side, the left-hand side. So in order for us to get to our goal, our vision, we'll need to figure out a way to get from this mess of imaginary and real to nicely separated. So that pretty much maps out perhaps what would be considered logical steps. So here we can say z minus lambda I. I'm going to start with the z minus lambda I. Notice I also would like to get rid of this fraction, because although the fractions manifest in the solution, they definitely don't manifest in this way. So here I'm going to multiply up this z minus lambda I. This would produce I times the z minus lambda I. And so the first thing to do from here would be to multiply this out. That would give me an IZ, a lovely IZ. So imagine I were to write up here, just to remind ourselves that this would give us something like IZ. And then if I do I times minus lambda I times I is minus 1, minus lambda times minus 1 would be plus lambda. So this would just end up with plus, and I'm going to just write plus lambda. So this here is what I would obtain by multiplying it out. So that is the result of doing I times z and then I times lambda I. So that would lead us to something that has everything we need to now move real and imaginary parts to their separate places. Before I do that, one of the most important things to consider is that the solution is z equals. That is z equals. So I want to remove or get together everything that has z in it and make sure z is alone. So basic algebra really. And in this sense, you can see IZ I'm going to put on this left hand side. So it would be minus IZ. The plus lambda will keep on the right hand side. The plus 6i I will move to the right hand side, minus 6i. And then what we have left here, you can see that this step here is simply that I've factorized out. This is just because I've then factorized out and have z minus IZ. Factorize out z, I'd have 1 minus I times z. Right, so that is how I obtained this here. Just in case I could write this here to make it clear what has happened, this is the equivalent of saying z minus IZ. And this part here, this z minus IZ, I've then factorized out to make the solution that we want. So why would I do that? Why do I want to have a situation where I have z minus IZ? Like I said, it's because my goal was to get rid of everything on the left-hand side that was not related to z, not a product of z or multiplied by z. Okay, so the next stage is we're going to, after factorizing out z, I'm going to divide both sides by 1 minus I. This produces z is equal to lambda minus 6i divided by 1 minus I. So this is what has occurred here. This has simply become the numerator, and this 1 minus I has become our denominator there. Now, here we are close but not quite. One of the main things to realize is that there is the capacity always in this situation where you have a complex number in the denominator to use a technique where you multiply the top and bottom by the complex conjugate. By doing this, you are breaking no laws, and you can see that one of the advantages to this is that if you were to multiply out the denominator, so to multiply top and bottom by the complex conjugate, I'm breaking no laws, but if I multiply out the denominator, so 1 times 1, 1 times I, minus 1 times minus I times 1 and minus I times I, then the only thing I would have left is 1 plus 1 in this situation, which would give us 2. All the imaginary parts disappear. The multiplication of these produces something of no imagination, and it is important to remember that relation. What you have is a capacity to remove any complex situation in the denominator by doing this pattern. And this pattern should be utilized over and over again, the multiply by the complex conjugate. This, like I've said, you'd have 1 times 1 is 1, 1 times I, minus I times 1, so those will cancel, and then you'd have your minus I times I, which will produce plus 1, and then that produces your 2. Now, the denominator, I'm using the same pattern, the numerator, I'm going to use the same pattern, lambda times 1, lambda times I, minus 6I times 1, and minus 6I times I. Once you do all of that, you can factorize the imaginary part out, and you are left with you are left with what would used to be minus 6I minus lambda I from this multiplication is simply now going to be 6 minus lambda multiplied by, because I factorized it out, the lambda plus 6 I'm going to keep together so that that is the real part, and it's all been divided by 2. Now, just as a point here, when I finally make this last part, you can see that there is no reason as to why I could have rewritten this as lambda plus 6 divided by 2 plus 6 minus lambda also divided by 2. That is the equivalent writing. Now, therefore, we can conclude by saying that the real part will be lambda divided by 2, so there's lambda divided by 2 is the real part, the lambda divided by 2 as described here, plus 6 divided by 2, and 6 divided by 2 gives us this 3. Finally, the same thing would happen here. You'd have lambda divided by 2 because you have minus lambda in terms of the I divided by 2, and you'd have minus 6 divided by 2, which is minus 3. And so that is how we tackle that first problem. Then it says, given also that arg of z is equal to 10 to the minus 1/3, calculate the value of lambda. So if I was to do that, there's a couple of things I would go through. First of all, I would consider that tan to the minus 1 opposite divided by adjacent, the opposite line is simply being said to be, well, we'll start with adjacent first because that's just how I've drawn it. We'd say that this is the adjacent of a length of 3, and the imaginary part, the opposite part of our triangle, if our triangle were to manifest as a shape like this, then the opposite part would be a 1. And so it's a relationship between opposite and adjacent. And it's saying that the one thing we can also recall from the question earlier is that the real part, which is the adjacent part of our triangle, so if I was to take this here, I would be able to add it to the diagram, saying, well, that is also the real part because it's the real x-axis of a complex number. So this is the real part. The imaginary part, that is which is multiplied or a product for I, the imaginary part, well, that is the opposite part of our triangle, so it will look something that looks like this. So what we can say is we can say the relationship between opposite and adjacent is equal to the relationship between lambda over 2 minus 3 and lambda over 2 plus 3. And that's what is being described here. And that is the result of looking at the Argand diagram for a complex number. Now, what we can do from here is we can simplify it down. So the steps to simplify are as follows. I can say lambda over 2 minus 3, lambda over 2 plus 3 is the same as, and I just multiply top and bottom by 2. This is very similar mathematics to the step earlier where we multiplied by the complex conjugate, and it was because it was the same thing in the numerator and the denominator is the exact same philosophy. So I'm just driving this home by giving it an algebraic or numerical version. 3 times 2 is 6. 3 times 2 is 6 here, so therefore we'd have lambda over 2 minus 6 over 2, lambda over 2 plus 6 over 2. The numerators I've collected, so it's lambda over 6 divided by 2, the lambda over 6, lambda minus 6 divided by 2, and lambda plus 6 divided by 2. And then because, depending on which way you've remembered it, but let's say, for example, a pattern that's quite consistent is something like top. I was to use a bit of color. We can say that this here is the top of the fraction. Let me escape for 1 second. This is the top of the fraction. This will be at the bottom of the fraction. This will also be at the bottom, and this will be at the top. And so, or top, like so. And so what we can say is, at the top, you'd have lambda minus 6, which you can see manifest itself here. At the top, there'll be a lambda minus 6. At the bottom, there'll be a lambda plus 6, which you can see is here, and because one of these twos is at the top and the other is at the bottom, they will cancel each other out. So that will leave us with lambda minus 6, lambda plus 6. So that is the one of the things to be aware of, therefore, is we're saying that this whole thing can be written as lambda minus 6, and this whole thing can be written as lambda plus 6, and it is equal to 1/3, or the relationship between the opposite and adjacent side, because this is tan to the minus 1 opposite divided by adjacent. Rearranging that, you end up with something very simple. 3 lambda minus 6 is equal to lambda plus 6, and lambda therefore is equal to 12. To conclude, the final part asks for the value